are not the only ones with a vested interest in the changes going on around Utqiaġvik. The National Oceanic and Atmospheric Administration, or NOAA, has been interested in the area around this town and have had a state-of-the-art climate monitoring system near it since 1973. This is a special type of NOAA facility known as an Atmospheric Baseline Observatory, or ABO. There are only 4 of them in the entire world, with the others located in Hawaii, the South Pole, and American Samoa. The purpose of these facilities is to observe atmospheric conditions in remote areas to avoid human intervention. What makes the ABO near Utqiaġvik special is that it is part of a clean air zone. Even though it is situated close to the town of Utqiaġvik, it is located upwind from it, meaning human activities don't affect their data. Furthermore, they are in a clean air zone that has no human interaction for up to 5,000 miles before it reaches the station. Additionally, they are the longest continuously running station in the Arctic, meaning the work they have done is some of the oldest record of how atmospheric conditions have been changing. While in Utqiaġvik, we were lucky enough to get a tour with one of the 2 men that man the station. His name is Bryan Thomas, the chief of the station. While here, Bryan gave us a personal tour about much of the equipment available in the lab.
That's our solar tracker. So the tracker has a motor in it, and it knows the time, and it knows the geometry, so it knows where the sun should be in the sky. So its job is to point at the sun. Those instruments on the tracker have a black ball that blocks the direct sunlight. So those instruments are watching for the diffuse solar radiation that's bouncing around in the clouds. And then on the yellow table that was down below, farther over that way, those are the ones that are measuring all the global incoming solar radiation. So you can take those 2 terms and put them in the algebra equation. And then the other one is, out back we have the albedo rack, which is the white rack with the 2 arms, and we're watching what's coming back from the surface. So now we have the other term in the equation, so we know what's coming in, what's bouncing around, what's reflecting back, so we know what energy is available in the atmosphere for chemistry to happen. So here we are. This observatory, again, is purpose-built for science, right? And so we have a building that we needed to make a room in this building for this instrument. This is the Dobson spectrophotometer. So spectrophotometer is looking at the color of light, and it's measuring the color of the light. And Dobson is the name of the person who was first credited with describing the amount of ozone in the stratosphere. That's good. Ozone is good up there because it blocks ultraviolet from the sun. When the ultraviolet is coming in from the sun, that ozone says no thanks, and so it goes back into space. What was noticed was that the ozone layer was thinning around Antarctica, right? There was this hole that was opening up seasonally around Antarctica. Well, it's still there, but it's not as bad. And one of the reasons is because after the hole was noticed, the countries of the world said, it's happening because of this bad stuff that we're putting in the atmosphere. Maybe we should stop doing that. And they stopped doing it. And now the ozone hole is recovering. And how do we know it's recovering? Well, we have the Dobson spectrophotometer to point at the sun and measure how much ozone is between us and the sun. And we have satellites that can look down at the ozone layer. And between the 2, we know what we're looking at. We know how many Dobson units of ozone we have. And what we do is we focus that light down into the instrument with this periscope. It has a prism, right? So focus the light down through here and then split it out, and we have the known and the unknown, right? And so we can measure the difference and measure how much of the ozone layer has interfered with the light from the sun. But every time we do it, we also have to do straight up because there's no sun straight up. And so that gives us an information about what the instrument is, how it's behaving without sun, right? Without a direct sun. So that's why we have the hatch in the roof. I won't open it because it's been wet and it will drip. So I won't open it. But, so I told you every once a week, people all over the world send flasks of air from where they are back to Colorado to be measured. We have our flasks here, and this is an example of what we use to measure. So this is our portable sampling unit. This is a briefcase. So you take it outside and you open up the briefcase that has 2 has two flasks. They're glass flasks. I'll show them to you in a second. Then you put up the mast, right? And this is just a fishing pole that telescopes, but it gets us up out of where we breathe, right? Out of that turbulent zone by the surface. So it's like a 5 meter thing. And then we pump the air into the flasks. And at the same time that we're doing it here, we're doing it on our intakes inside that come down off our tower. And that way we can compare those 4 flasks together, and if there's any difference, then we try to explain the difference. So here's an example of the flask that we use for this measurement for carbon dioxide and methane. So it's glass, it's blown glass, and the tape over it is just to try to keep it from shattering if it were to break. And then it has the inlet and the outlet. And so when we connect them, this comes from the pump, pumps in, and then it goes out to the second flask, right? So they're gathered at the same time. Notice they have a screw closure, so we can open them and close them more than once. This apparatus is not super sophisticated, right? All you have to do is take this out, you charge the battery, and then you take it outside, you put up the mast, you turn on the pump, you set it to flush mode, right? So it's gonna go through the pump and just go out and go back out. And then after you flush it for a while, you've gotten that clean air through the flask, then you decide to sample, you put that lever down, you walk away, and you come back, and it's at pressure, and you close it.
Overall, the purpose of these measurements with all of these very precise instruments is to track changes to our globe caused by human intervention. Greenhouse gases are a major part of this change occurring.
Of this graph, the last time we saw this much change would have been a 5,000 year period at the end of the last ice age. And on this graph, this much change would have happened over the span from there to the truck. Right? It was really, really long, really, really gradual change. And in contrast, we've seen this huge explosive change just in the last 50 years. So we have a lot more greenhouse gas in the atmosphere than we did. And that means we have a lot more heat trapped in the atmosphere than we did. And we're seeing the effects of that even today, right? We're seeing heat waves in Europe, we're seeing wildfires, we're seeing floods, we're seeing all kinds of effects of more energy in the atmosphere. And that energy is heat trapped from coming back off the surface of the earth when the sun heats it, right? So, and greenhouse gases are what's causing that. This is just one of the greenhouse gases. If we were to put any of the other ones, you'd see a similar trend, up, up, up.
One of the changes caused by climate change in the immediate area is permafrost degradation. This reminds us that at the end of the day, we are battling climate change, and as researchers, it is good from time to time to take a step back and look at the whole picture. Gaining the understanding that we are part of a much larger community of researchers, all looking to navigate the world through a large change and better understanding our place and impact.